Hello. LDISKFS is still very popular, fast, and fault-tolerant LastFS backend. And it is ready for any new problems, and I will show new problems that arise and that can be overcome. At some moment, file system is filled and blocks are fragmented, so it can behave a different way, and some unusual activity can be seen. So one day we noticed, our customer noticed that the action that that usually takes only 12 seconds takes 12 minutes. So it's a very, very large performance degradation. So before this moment, the speed was 700 gigabytes, but at this moment it was only near 12 gigabytes at seconds. This is 6,000% decrease in performance. Also, some fragmentation is noticed, and write performance degradation. But read performance is the same. So we started this investigation, get some data, some crash dumps, and understood that the LDISKFS block allocator is the reason of such write performance degradation. So at this moment, we see that block allocator started block groups scanning from group 75396 group, and processing all groups, and currently processing group number 8. So this is very large target, a lot of block groups, and this is the reason why this symptoms has been seen. The problem is that allocator tries to optimize block allocation. So even if not so large range of blocks are requested, it tries to increase allocation window every step. So at the left side of slide, we see how this goes at the system, then a lot of free blocks. So first time we get small chunks of blocks, then increase it, and increase it again. So this gives a nice performance improve of block allocation. But for aged file system, this algorithm doesn't work, because at some point allocator optimize its request, but cannot find a group with enough free blocks. So he processing all block groups starting from goal and until the end of partition. And if a lot of block groups, much time is spent. To understand why block allocator behaves such way, we need to understand then it is enabled and what it does. So body allocator starts to pre-allocate blocks if it hasn't find pre-allocated blocks in inode pre-allocated group or in locally pre-allocation range. It pre-allocates in locally group if file is quite same to have small files in the same group, and it pre-allocate to inode if expect that large file is written. So if pre-allocator didn't find the pre-allocated blocks, it pre-allocate new range of block. First of all, it normalize request. What does it mean? It means that it allocate not requested size of blocks, but normalizing it adds some, make some assumption how much blocks needed and allocate a lot of blocks. Then it add pre-allocated blocks to inode pre-allocation range or group pre-allocation range. Body allocator has 4 loops, so this means that it processes all partition 4 times. At first loop, he tried to find quite large range of blocks. That is power of 2. If it hasn't found a good group for such pre-allocation, it starts second loop that search for group with average free range equal to requested size. On third loop, it just finds the group with range with requested size. And on third loop, he gets the first group that has any free data. Also, there is optimization from LDISKFS that adds a pre-allocation table, and this normalization is made based on given numbers that called pre-allocation table. So then this problem arises. Anybody said that LDISKFS and ext4 already has some tunables that can help to solve this problem. This tunable is called MB min to scan, MB max to scan. This is good tunables, but they are not about this problem. These tunables are used to then appropriate group already found, and then extend scanning in progress. So we need to add some tuning for this block group scanning to solve the problem. Also, there are some statistics that are shown for allocator work, but this statistic is not enough, so we need to add some other numbers to estimate how we improve allocator work. So 2 solutions suggested. First, doesn't require any LDISKFS code changing, and second one is requires some patching of LDISKFS code. First of all, we could change pre-allocation table and exclude some numbers that are not real, that are not be used during block allocation. I will show it later. And second, we can skip loops that which doesn't give results. So if no enough block groups that with free range of power of 2, we can skip loop 0 and move to loop 1. Also, we can start from any loop. So relocation table is existing, can be viewed and changed in proc.fs. This file is called prealloc table. We can build new prealloc table based on MB groups output. MB groups gives the table that shows how many ranges of any length exist for every range length. So we, based on this information, we can generate a new prealloc table, upload it to proc.fs, and after this moment, during MBalloc normalization, block allocator will never get too large preallocation window. And the idea is periodically adjust this table, so cluster will have appropriate preallocation table at any moment. So how this works, and a little test of this approach. So let's give special large numbers to preallocation table and upload it to proc.fs. Then make some copy to file and estimate the write speed. So some numbers are read here. We see that 2,000 extents were scanned, and 10 scanning was broke because of tunables of maximal extent scanning number. So this showed that some extent scanning process was useless and was finally broken, so interrupted. Now we adjust this preallocation table using a script that gets output from MBalloc table, and some large numbers in prealloc table was reduced. Now block allocator doesn't try to allocate to large ranges, and there are no broken scanning at all, so 0 breaks, and less extents are scanned. And writing speed is about 20% faster. So to make such a solution, some bugs in LDISKFS need to be fixed. LDISKFS changed the ext4 sources to add ability to change this prealloc table to output it. But changing of this preallocation table is quite racy, so we have noticed that changing of this preallocation table leads to fault. This code was simplified. Now preallocation table has fixed size, enough large to store usual case table, and now it works. So second solution, change ext4 and LDISKFS code and allow to skip any loops that we want. So based on the FS condition, we can decide that no reason to process whole disk in loop 0 because no enough large 3 blocks range there. So we say start from loop first or even from loop second. And the decision if we need to skip loops is based on partition-free space. So it's quite simple heuristic, but it works in most cases. How to use it? There are 3 numbers that show the percent of partition filling. So in this slide, after 75% of partition is filled, loop 0 start to be skipped. After 85%, loop 1 started to be skipped. And there is 95%. From this point, second loop is also skipped. Also, some lines added to a statistic, these useless loops and skipped loops to see how much loops were made by allocator without success and how much loops we skipped because of this optimization. So we tested it on a quite large partition, about 100 terabytes OST. We tested it on LDISKFS only, without any other lustre effects. So before fragmentation, then it is quite empty. This disk, the writing speed is above 1 gigabyte per second. The read performance is also good. But if this partition is quite fragmented, performance drop is catastrophic. So it's, as shown, 6,000 persons. So it's only 10 megabytes per second. We fragmented a disk quite artificial way. We used debug.fs and made 53 blocks, 50 occupied, and so on, to wall of the disk. So now let's check our solution and enable loop 0 skipping. So for this we sent 50% to C1 tunable. Nothing changed because skipping C0 loop doesn't help, because no even range with average range in a group. So partition is too fragmented. Now we try to skip C1 loop. And after this step, the performance returned to half of original. This is a good number because of high partition fragmentation. So we can restore the most of writing performance using this approach. So as I said, that we decision made based on information about how much free space on partition. This is quite simple heuristic, and other heuristic was suggested. For example, we could disable loops at moment when no good group was found, and enable it then some free space returned to this partition. So this slide, state machine shown, the top part of state machine with four states. And other way, quite the same. We disable if no good group found, and enable it based on MB stats table information. We can use other. We could use other heuristic. We could use other solutions. For example, big alloc-XT4 feature. Yes, it can solve the problem somehow, because less groups, less metadata, so less time spent for allocator to process them, but but this improvement not dramatical. I believe we can reduce time the same number as time we make cluster larger. Other way is we could optimize body allocator loops and try to make one loop from third. Probably this can help, probably not. We didn't try this, but just idea. Also, we can say the maximum 3 blocks range and use it during allocation. Also interesting idea. So, summary. Patch for loops allocation skipping is already tested and uploaded and submitted to Jira. This is LU12103. It adds some statistic output and based on free space heuristic. Based on XT4 discussion, I understand that XT4 is not ready to land this patch how it is now, because average XT4 user doesn't want to tune anything. So he doesn't want to set these numbers. He wants that everything works from the box. So any good heuristic need to be used there. So the discussion in progress still. The first approach of this pre-allocation table is now tested on real cluster environment. That's all. Thank you very much. Any questions?
So Artem, those suggestions you provided at the end, the 3 other options that you're thinking about doing, are those? Do you want to? Are you planning on going ahead and implementing those?
So currently, I'm going to lend this patch to Lustre, to our main tree, and probably make any other heuristic and lend it to XT4. Now, currently, this solves the problem what was reported by customer, even with such solution. So if new problems will arise, new solutions will suggest it.
No, but you had 3. whatever, 3 slides ago, you had, one for that.
This one?
Nope, back up.
Back.
There we go. Those 3.
Uh-huh.
Right? So those look like good ideas, right?
Yeah.
So are you going to work on those?
Yes, actually, because this is the most smart way, I believe, but most complicated, I believe. Yeah, so actually we started to find a good architecture for this. So.
Other questions? I have one. The tweaking you have presented, they are implemented by your patch, or are they already existing in Lustre? The LDISKFS tweaking you presented, are they part of your patch, or are they already included to Lustre?
Actually, the most of this idea are in this patch that in Jira. And the pre-allocation table idea doesn't require any code. It is in this presentation. Everybody can write simple script. So if you want, use it.
I think the question is the parameters that you described in your slides, the LCTL parameters. There were a few of them in your slides, and I think that's what Thomas is speaking about. No, the parameters, the things you can configure.
Configure?
The parameters.
The threshold tweaking?
Also, the patch that fixes pre-allocation table changing is already landed, so it can be changed without dangerous faults.
Do you have other questions? If not, thank you, Artem. Thank you.